Hello everyone, welcome to a 10 minutes algorithm class. Today we'll talk about the simplex algorithm for solving linear programming problems. So what exactly is linear programming? Linear programming is a method to achieve the best outcomes such as the maximum profit or lowest cost in mathematical model whose requirements are represented by linear relationships. It has applications in lots of different areas. Here is a real-life example. You may pause the video now and read it first. Then try to list out all the constraints mentioned in it on your own. Here we introduce three variables, x1, x2, and x3, to represent the number of units we're going to produce for model A, B, and C. We know that there are constraints in three aspects, namely production capacity, assembly time, and packaging hours. Knowing that our goal is to maximize the total profits, we end up with the following linear model. Actually, this is a linear program. We'll then talk about how to apply simplex algorithm to get the optimal value for the objective function in this linear program. Simplex algorithm is an algorithm used for solving problems in linear programming. It takes a linear program in standard form for simplex algorithm and returns an optimal solution. Let's first look at what's the standard form for simplex algorithm. We say that a linear program is in standard form for simplex algorithm if it is of the form as follows, which satisfies three restrictions. First of all, the objective function is a maximization rather than a minimization. Secondly, all variables have non-negativity constraints. And lastly, all these constraints are inequality constraints with the same sign, namely less than or equal to. Since simplex algorithm only works for linear models that are in the standard form, we need to formulate the program in a way that fits the requirements. Fortunately, any linear model which is not in standard form can be easily rewritten in standard form. If the objective function is a minimization, we can easily convert it into a standard form by negating its coefficients. If a variable does not have non-negativity constraint, for example the variable y in the following linear program, in this case, we can simply substitute the variable y into y1 minus y2, where y1 and y2 are both greater than or equal to 0. Then we have a linear program in standard form like this. If there exists equality constraints, we may simply replace it by two inequalities, one with the relation less than or equal to, and the other with greater than or equal to. And if there exist constraints with different signs, we can simply negate it. Now let's have a look at the pseudocode for simplex algorithm. Don't worry if you feel it's a little bit complex at the first glance. We'll use an example to explain it. Hopefully it will become clear to you later. Simplex algorithm consists of two parts. The first part is to convert the linear program from standard form to slack form and get a basic solution. Second part is iteration and return the optimal value for the objective function. Now let's have a look at an example. Here we have a linear program in standard form. The first thing we need to do is to convert it into slack form. Let's have a look at what the slack form is and do the first step of the algorithm. Slack form is a form in which non-negativity constraints are the only inequality constraints, and all remaining constraints are equalities. For each inequality constraint, we introduce a new variable called slack variable and rewrite one inequality constraint into two constraints. We use the variable z to denote the value of the objective function. We call the resulting format slack form. Now, you can pause the video and try to convert the example program into slack form and check if you did the right thing. So here on the left-hand side is our original linear program in standard form. To convert it into slack form, we first add the new variable z to denote the value of objective function. Then we start the operations for these inequality constraints. Since the inequality relations are less than or equal to, and what we want to achieve is an expression with no negative value so that we can introduce a new variable and set its value to be equal to the expression, which is greater than or equal to 0. We observe that if we move the left-hand side of these inequalities to the right-hand side, we can get what we want. So for inequations 2, 3, and 4, we move the left-hand side to the right-hand side. We then introduce three new slack variables, x4, x5, and x6. Finally, we end up with the linear program in slack form on the right-hand side of these arrows. We call the variables on the left-hand side of these equations basic variables, and the variables on the right-hand side non-basic variables. At this point, we can get a basic solution. A solution is said to be feasible if all these variables are non-negative. Therefore, we can say that this solution we get at this point is a basic feasible solution. the value of our objective function is 0. Something we need to declare is that, in this video, we assume that the basic solution for our input linear program is feasible. However, in some cases, the initial solution may not be feasible. You will need to apply an algorithm called initialize simplex algorithm first, to return a slack form where the basic solution is feasible, and then use the simplex algorithm to gain the final result. Now we've already finished the first part of the algorithm. Then we can start the second part, which is the iteration. So basically in this step, we're just manipulating the slack form we get from the first part. In each iteration, we reformulate the linear program so that the objective function has a greater value. Every time, we select a non-basic variable xm, whose coefficient in the objective function is positive. We call this variable the entering variable. Then we increase the value of this entering variable as much as possible, without violating any constraints given by the linear program. The entering variable xm then becomes basic, and some other variable xm becomes non-basic. We call it the leaving variable. The value of other basic variables and the objective function may also change. We find the tightest constraint for the entering variable first, and then switch the role between the entering variable and the leaving variable. If the tightest constraint is infinity, we say that this linear program is unbounded. If it's not the case, we substitute for the entering variable in all other equations. In this way, we rewrite our linear program. This operation is called pivot. Each iteration is basically just a pivot operation. We then repeat this operation several times until we reach a state where all non-basic variables have a non-negative coefficient in the objective function. At this point, the maximum value for the objective function is reached. Let's go back to the example and do a pivot operation together.
First, we need to choose the entering variable. There are three choices, x1, x2, and x3. Since they all have positive coefficients in the objective function z, you can choose either one. In this case, I picked x1. The next step is to calculate the bounds for x1 by dividing the constant term with variable x1's coefficient in each of the equations. We can increase x1 to 40 without causing equations 2 and 3 to become negative, and for equation 4, x1 can be increased to 48. The tightest bound is 40, and it corresponds to equation 2 and 3. You can choose either equation and the algorithm will work. I have picked equation 2. In the next step, we rewrite equation 2 in terms of the entering variable x1. And lastly, we substitute this new equation for x1 back to obtain a new set of equations. This will eliminate x1 from the linear program. You can see the detailed working and the final result on the slide. x1 becomes a basic variable and x4 become non-basic. Now you may want to pause the video and try to solve the rest of the problem on your own. When you have finished, you can start the video to check your answer. Looking at the objective function, we see the variables x2 and 3 have positive coefficients. This means that we haven't reached the optimum solution. So let's apply the pivoting operation again. This time we can pick from x2 and x3 as the entering variable. I picked x3. Again, divide the constant term in equations 2 and 3 by coefficients of x3. We find the bounds at 24, positive infinity, and 24/7. Notice the coefficient of x3 in equation 3 is positive. This means that x3 can be any positive value and will satisfy the equation at non-negativity constraint. This time the tightest bound is 24/7 given by equation 4. As we rewrite equation 4 in terms of the entering variable x3 and substitute this new expression for x3 back into the slack form, we will obtain a result shown on the slide. Basically, we perform the operation again by setting the entering variable to be x2 to obtain the final answer. This is the optimum solution since all of the non-basic variables in z have negative coefficients. We are able to read off the values of the final slack form by taking the slack variables x4, x5, and x6 to be 0. The final solution is that we can have the maximum profit of $892 from producing 36 units of Model A, 2 units of Model B, and 2 units of Model C. We hope this example has helped you to have a concrete understanding of the simplex algorithm. The pseudocode for the iteration step and the pivoting operation are given here. You don't need to remember it. You might be wondering how fast simplex algorithm runs. The answer is that it depends on the inputs. In the worst case, the algorithm will terminate in exponential time. You might think it's really slow, but in practice, this rarely happens. The simplex algorithm is quite efficient. On average, it runs in polynomial time. That's all for this video. Thank you for watching.